Нет, столбик я могу переворачивать. Столбик я переворачивать. Тряпка есть, мел есть.
We will wait 5 minutes. Okay, probably I should start. So today we will study differential forms on super space. So the plan would be as follows. First, I will start with differential forms on manifold. So it will be a review material. And then I will introduce algebraic. It's called scalar differential. So these scalar differentials appeared when Keller was a student of Zariski, and he was trying to understand what are differential forms in differential geometry. So he went to Grothendieck, he talked to Grothendieck, and he came out with some concept. And now we will study algebra of differential forms as an example of supercomputator. And then we will do generalization of this concept of a differential form in superspace. That are not set of points, as I explained before. And you will see that this approach 4 would be a very drastic generalization of approach 1. So this is due to Arnold. Mathematical methods in classical mechanics. And if you will have time, I will go to Berettin integration. Once again, all of this is a preliminary material to study of topological theory. So what was the Arnold points of view on differential forms? He said the following. Suppose we have space X. And suppose we also have the space functions F from X to R to C to any. Let us take a product of these two spaces. So element of this space is function f. Element of this space is a point p. He said, evaluation map. To R. It takes a pair P F and brings F of T. So far, so good. Now, he said, point is just one of the figures. Let us generalize from point to other figures. In particular, there is a line. Gamma. We would like to construct a map from gamma and something to real numbers. That will generalize this. Idea. Let us generalize space X where point is. To the space of formal linear combination. So why we are going to do this? Because on the space of figures, there is an important concept of a boundary. And boundary of a figure could be not just one point, it could be a set of points. And also it is a set of points with sides. So that's why here we would like to consider this formal linear combinations. We would also call this figure. And also f could be generalized. F from such figure is this. Now we want to consider curves. What can we do for curves? First, we consider formal linear combinations of curves. So we allow this. Second, we it is because we are going to take a boundary and we need to know orientation of the boundary. Third, we would like to have this F map. And we would like to say that F map of curve gamma would be equal to M of gamma 1 plus M of gamma 2. Gamma would be cut into pieces. Gamma 1, gamma 2. So that's what we want. Now we know how to construct this F. We take curve and we cut it into small pieces. So in order to construct this F, we need to know the value of this question mark in gamma A. So if you think a little bit, you would see that gamma A would be considered as tangent vector. So this thing is nothing but function of tangent vector. And if everything is smooth, we call this one form. One form. Function on tangent vector. And this is the concept of differential form. And evaluation of gamma. So how do they put it? Of gamma omega 1 is defined to be the integral over gamma of omega 1. So that's how we have this concept of differential one form. Now we have different figures. These are also figures. Two dimensions. It also could be cut into pieces. From this smaller piece, we say that it is something like parallelogram formed on the vectors gamma 1, gamma 2. So this question for purposes is is a function on what? On what describes a parallelogram? On external product of V1, V2. And then that we will call formula 2. And then evaluation of the surface sigma and omega 2 we will define as an integral of omega 2 and here we will see just. Now this is a way how we define differential forms in the form of Arnold. What can we see from this? So there is an operation delta on figures. It means data bound. It has a property that if you compose it, you will get 0. So simplest example is given by Andrey. So A and B are points, gamma AB is the curve. It is a geometric theory. And in this way, we can define on differential form as a conjugate to delta. Please note that I am explaining everything without involving coordinates. It's a geometry. So geometry is not something when you are writing down things in coordinates. Geometry is something where you are drawing pictures. So what does it mean? It means that for any sigma, we define D in the following way. So you may think that it is a Stokes, Newton, Leibniz, Cauchy, and many other people's theory. It's not from Arnold's point of view, it's not a theorem. It is a definition. You apply d 2 times, you have delta squared. So what is the theorem? The theorem is how to compute it in local coordinates. Suppose that the big manifold X with coordinate X mu. Then we know what the function is. We need to know what differential form is. So first of all, let us consider basic differential form. Dx mu. How would we define them? Okay. Let me draw this manifold. So here I am drawing because it's a geometry. Let me take a point P. Let me take a coordinate x mu. And let me do a shift of point P in coordinate x mu. It means that I'm shifting x mu to x mu plus epsilon. Here mu is fixed. And I call such thing vector v mu. How you can imagine this vector? I give you another geometric picture. Imagine that this manifold X is embedded into some space Rn. Take a base point 0. Then you have this radius vector. It's a function of x now. So what is this? V. Now I'll try to imagine this vector field V mu as dr over d. this is called external geometric point of view. When people are doing internal geometry, they say that V mu is somehow associated to P over Ts. But at that moment, now, I prefer to think in external picture. So anyway, we understand what that means. And then we take dx mu by the following definition. Now, what we know? We know that if we have a differential form, we can multiply it by function f. You will still get a function on small pieces. That's why a general one form could be expanded in these basic one forms. Later on, I will omit the summation index. I will use so-called Einstein rule, that if I have repeating index, I sum over it. This is related to description form. And this omega use I will call components of differential form. Okay? This is about one form. What about two form and higher form? Omega 2 would be decomposed. Okay, I told you that I'm not going to use this summation index. So what is this for? Would be defined such that this evaluation vector on V mu prime of H V mu prime. So now you understand that V mu prime is just a piece of the surface. It will be the definition. So all differential forms in coordinates could be written in such form. And now I told you the theorem is how to compute in local coordinates. I already defined it. I already defined everything. The only thing that is missing is the computation of this d in local coordinates. So you introduce local coordinates and you compute. I'll write it here. This is anti-centralization. So this is actually a theory. So how can I formulate this theorem? I can formulate this theorem in the following way. Consider external algebra. Generated by dx. Then d is from 0 to taking external. Okay, so I gave you a review of the theory of differential forms and their structure, and I even presented you the main theorem without a proof. Also, remark. Differential forms supercommutative algebra where this is multiplication. And D is an odd derivative. In this way of presenting things, I heavily rely on local coordinates. I heavily rely on the concept of figures that are made of points, their boundaries, etc. But this is how it works on manifolds. In this way, it would not go to superspace. We need something more algebraic. So, when Keller started it, he was motivated by trying to write down something on algebraic manifolds, on algebraic spaces. So what was the motivation of Keller? He wanted to describe something on spaces that corresponded to the algebra of C, the1, Dn, and here factored by ideal generated by some functions at A. The reason he wanted to do it was that this may not be a manifold. It may not be locally a disk. It could be something else, like it's not a disk at all. It has only one point. And this was even before we go to this superspace. if these F's have some singularities, so it would also be not locally a disk. But Keller had an idea that the concept of differential forms could be modified. So here we need to go to something algebraic. Okay, so I will erase geometric picture. And go to something algebraic. So Keller says, suppose we have a commutative algebra. We would like to consider differential form. What would they be? He said, let us consider one form. How to construct one form. He said, let us start with what would be a Durand differential. And let us call the symbol D. We would like to have a map from functions to one form. So what could it be by analogy? dA should belong to one form. Now we know that we may multiply differential forms by a function. So A0 dA1 should also be a differential form. However, if we will try to say that differential forms are just pairs of two algebraic elements, it will be too much. Because we have an example. For C of Z, we should get only VZ, VZ, Z2VZ, so number of differential forms in this example of one form should be the same as the number of elements of the algebra. And here we have twice. So why do we have so many? It's because he said, here we have an equivalence relation. Actually, D A0 A1 equals, but we will say that it is equivalent to A1 dA0 plus A0 dA1. So here we have the space of pairs factorized by equivalence relation. And the equivalence relation is that A0 dA1 is equivalent to to the pair 1 A naught A1 minus A1 A naught. Okay. We can go in this way and say, let's say omega 2. At the moment, dA1, dA2 are just symbols. So we have the following thing. Instead of writing down factorization here, I will write factorization here. What is omega dot? Algebra, supercommutative algebra. By even and odd, by even elements and odd elements. Yeah. But we need to take a quotient by ideal, and the ideal would be AB minus B minus AB. And this is a definition together with the differential equation. Now immediately I will give you an exercise. Exercise. Consider C of V1, V2. Compute the space of differential forms. Okay, I'll use this mathematical word spectrum. Spectrum is a space associated with the else. So it's a homework, number one. Now, this polynomials of two variables is not the only commutative ring that we may consider. Consider the following construction. I take polynomials and n variables. I divide it by ideal generated by a single function f. The question is how to describe, so let me call it AF. How to describe differential function, differential on spec AF. So I need to write it down because I use the word spec. In algebra geometric correspondence, we had an algebra A and we had corresponding space X is called fact A. How to describe this? How to describe this space of differential forms? So without this, we expect that it will be a supercommutative ring. That are functions of z1, zn, and also dz1, dzn that are odd. Now here it turns out that we have to divide by the following ideal. Definitely, it should have f of z1, zn, but also, and it's important, we would include df. That is, by definition, dz a df over dz. Now there is d on differential forms. You can use scalar construction here on the left hand side, on the right hand side. This ideal that we quotient with is invariant under the action of D, because df is also an ideal. So let me call this 2, check. So that 2 is equivalent to Kevin. And this is homofinal 2. And here, check this for, say for n equals to, it's a homosign. Interestingly, here we have another example of supercommutative algebra. And it is a supercommutative algebra with differentiation D. Moreover, it's homological differentiation. This D squares to 0. All this is to give you examples of supercommutative space. Otherwise, I said, consider just supercommutative space. You may think, what the hell it is, supercommutative space? This is supercommutative space. Now let us come back to A. And remember that we have dA, derivative of A. I just remind you that dAB was dAB plus AD. And I told you that, okay, I have not told you that. Now I will tell you something. Define the iota action of dA on differential form on spec A. So how can we define? In differential geometry, B was something like this. But now I say that I'll define iota action. So iota action in differential geometry is I will write it in components. So I start with the n form, and I am getting n minus 1 form. You see, it's called with this letter iota, and probably you have not heard about this iota, but that's why it has such an ugly representation as iota. It's called internal contraction. But this was on the manifold where we had local coordinates. However, it's possible to define the iota action of differentiation on differential forms. And of course, we will define it in the following way. First of all, iota b applied to A is equal to 0. Iota b applied to dA. So this is one form. It should be a 0 form. And answer is purely algebraic, it's just dA. And we will say, look, iota t is promoted or derivative of the or differentiation of the supercommutative algebra. And once again, when I'm writing this definition, I do not have coordinates. I specifically put places where I have coordinates in the special boxes. Because in general, we will not have covering by disks, we will not have coordinates, we will have only this. Let me also define LD action of D. LD applied to A should be dA, and LD applied to dA should be dA. And also LD should be differentiation of and this is algebraic definition of the V derivative. And now there will be home assignment 3. Prove magic Cartan formula. And magic Cartan formula is IB D plus DIV is LC. So let me see the time. I spoke too much. But there should be a break. But if you'll be a mathematician, pure mathematician, you would see that what I described to you, the Keller part. How to explain the ramp differential, vector fields, differential forms, contraction, Cartan magic formula in purely algebraic terms. Such that when you go to the manifold that has coordinates, you will get formulas that you can read in the text. Probably we will do the following. Probably I will speak a little bit more right now because I don't want to make a break. And then we will make a big break. Okay? So, when I explained it to you now, in the commutative context, there is one more thing that you may do. And this extra thing that you may do is say, hey, how commutative is important. We can do everything in supercommutative case. If everything is algebraic, we can do the same thing in supercommutative case. So in what I explained to you, just replace properly. Commutative algebra A by supercommutative. and you will get the theory of differential forms on the supercommutative space. So what would change? We should have signs in the concept scalar differential forms. Remember, we started with A naught dA1. And we were trying to factorize it over dA naught A1 minus dA naught A1 minus A naught dA1. So if you would like to understand this in terms of pairs, when you make such transformation, you say that this dA naught A1, it should be minus, and here I should put minus 1. Here parity of A1, parity of A0 plus 1, because here I have dA1, A1, dA0. Such that all differential forms, at least one forms, are the forms A naught dA1, ADB. Okay, what else would change? Remember that here we have an extra minus. Now let us see how can we or should we redefine this. So the question is if we should put plus or minus here. According to the general rules of supercommutative algebra, B has a parity. And also this thing has a parity. Wow. So what I'm doing here, I'm trying to change these things together. Probably it is better to give it to you as a home exercise. Yes. Because if I'll try to do it in front of you, you will say, oh, some signs, etc. So, but if you try to do it by yourself, so home assignment number 4. So in home assignment number 4, you should try to fix for Cartan magic formula. It's interesting to see what is this ID. Okay, I will give you a hint. For ordinary manifolds, iota is so you don't often see it in this way, but it's exactly what happens if you understand the differential forms of the superalgebra. So that's why that for ordinary manifolds, parity of iota v is 1 because of this d. Now for supermanifolds, you will have the same thing. However, let us see how the parity of this thing goes. It comes from this v mu, it comes from this x mu, and it comes from this d. You have to combine parity from all this, from all 3 sources. In particular, why in Cartan magic formula we have plus sign? Because we have ID and D. So this is odd. This is odd for ordinary algebra. However, here, in general case, you need to combine all parities and derive Cartan magic formula. Let me be more precise here in this comma sign. Consider as complex numbers, and here we have some coordinates y1, y. and where parity of y would be either 0 or 1. Now, describe these explicitly. And find them here. Describe differential forms. As and construct sections of D on omega tilde and see derive a version of Cartan magic model. So the version would be I, B, D, and here is plus minus 1 to something. And here is D, IB equals LB. So the question is to determine this minus 1 to this unknown power, be 0 or 1, depending on this D.
I wonder if this sign will be on the first term. Because, like, if we act on element A, then the second term will not matter actually.
So you want to say the following. You want to say that probably here could be a sign. Okay. So okay, determine all signs. So here assume that B would be properly anti-commute or commute with ID. Then the question how to determine it. Try to determine the parity of this ID. It would depend on what? In commutative case, the parity here is 1. That's why here we have commutator. But if D has a parity, we should have change in parity. So I give you this as an exercise in science. let me summarize. I kind of constructed for you the theory of differential forms in two ways. First way was differential geometrical, just to give you a warm-up. And second way was algebraic. And it is algebraic way where you can go to superalgebra description. And of course, in the superalgebra description, whenever you have dy, the parity of dy is 1 plus parity of y. In particular, it means that if you have odd coordinate, you can have differential forms of infinite rank. And it's normal. You should not be afraid. And here we are coming to the very interesting topic. Okay, so I'll take some time from the break. And here we are coming to the very interesting topic, and this topic is that if we have a super space, we do not have an integration procedure that was previously integration of the top form. Now we have to define it in a different way. And that will be the topic that we will discuss after the break. Okay? So now we will have a big break, like 20 minutes, because I spoke a lot. Now it's 4. Okay, so we will resume at 5:15. Okay. Now I'll talk a little bit about spaces. So suppose we have an algebra of polynomials of n variables. It's an algebra. So what is the spectrum of this algebra? It's a geometrical space. And my statement is that this space is Dn. I'm just recalling it. So what is the maximal ideal? It's a space of polynomials that vanish at a point in particular for n capital equals to 2, I can write down this ideal in the following form. It's a space of polynomials x1 minus x0, 1, and here I want p1 plus x2 minus x0, 2 polynomials p2. It's clear that it's an ideal and it corresponds to the point. Arguing in this way, you may show that the spectrum is exactly the space Cn. Now, consider C of odd coordinates. So they are odd. So this is isomorphic to external algebra. of here. So here that means that this space of polynomial is the same as a symmetric algebra. Such space is called Pn shifted by parity by 1. In the sense that coordinates are shifted by parity by 1. Or sometimes people use the following. Now let us consider the manifold X and the tangent boundary for X. Such functions on Dx may be expanded in coordinates that I will call y nu of the phi. So at least locally, it is functions on X, and here I will get symmetric powers of, let it be, phi plus v max. I just mean that any function of X and Y would be expanded as f of X. Okay, so here I have this Feynman rule, sorry, Einstein rule. And these coefficients f are symmetric. Under permutation of phi L plus phi B. Now, let me look at the algebra, that is the algebra of differential forms on X. So this is external algebra of CM. That's why of the algebra that's branching from the text is what? Is E shifted by 1 or the same if E. It is the explanation of kind of trivial fact that you may consider differential forms as functions here. And later we will widely use it. Now, I will come to the issue of integration. In an algebra. Goal So what does it mean to define an integral? It means that if I have an object f I would like to get a number. I would like to have some prototypical example when I can do it. Suppose I have S1. Let me take 5 angular coordinates. Then to any f that belongs to function on S1, I may associate the integral. So this is a unique symbol. There are many ways to do it, but I will propose the following. The way that I propose would be possible to generalize to the super case. Let V be a vector field that presents the measures we know these vectors. Then, what we know about the integral? I know that this thing equals because LV preserves the phi. V iota V phi G plus iota V V. So now this term is 0 because S1 has no boundary. Now what about this term? IV of something has a degree definitely less than degree of S1. So this term also equals. So it means that integral of d phi over S1 of LV of G equals to V. So what does it tell people? So what does it tell me about the integral? Let me take it. Okay. So here sum goes from n from 0 to infinity, and here sum goes from 1 to infinity, because the sign of 0 phi equals to 0. Now what can I say about this? I can compute the kernel of this. How can I do it? That's why this term would be mapped to 0. They are in the image of LV. Now let me look at the first step. For n non-equal to 0. It means that all terms with n non-equal to 0 would go away. So it means that only psi naught times constant term would survive. From this definition, I do not know coefficient in front of this term. But I can put it to be equal to 1. That's how I'm determining this integral. And this is exactly the same that you will get using any other approach. Now let us go to odd case. We would like to define these terms, and here we would like to put f of theta. So we are interested what it is. And here we expand. As a vector field, we will take the only vector field that is available here is d over d theta. So f naught is d over d theta of theta f naught. That's why this term would be integrated to 0. If not, so that's why we need to fix this integral on this f. And we define it to be f1. And this is Berezin integral. I can easily iterate I would like to try to understand this integral. So I may expand here. F naught plus fi theta I plus f1, 2, theta 1, theta 2. When I take integral over theta 2, this term goes away. From this term, I will get f2. And from this term, I will get f1, theta 1. Now I take the second integral. Now this term goes away. And the result is f1. This is how we can take the Berezin integral. actually Berezin integral was discovered Berezin not from these formulas. Berezin was interested in understanding fermions from the point of view of functional integral. So there are fermionic fields, and there was a physical rule of sum minus 1 to the number of loops. And he was trying to reproduce this rule, and he guessed it. But this explanation, I think, is purely mathematical explanation, not involving physics at all. Now let me come to the most interesting formula here, namely the integral of differential form of degree n over the space x with the dimension of x equals to n. So we know that it is, in geometrical approach, it was something that was canonically defined, without any choice of coordinates, without any use of them. But let us do instead the following. Let us understand omega n as a function of t shifted by 1 to x. And let us try to understand it in the following way. We need to take integral over the fiber and then take integral over the base. How does it work? Let me propose the following formula. Choose coordinate system on it. You see, I'm very rarely using coordinate system today. But here I would like to do it for a moment. Excellent. With the help of this coordinate system, I get coordinates on P1 to the point P. That are dx1, dxn. So I would like to decompose my differential form as omega I1 In over x. Now x is the point in x, and here I would like to take an integral over the fiber. And here I will do the following. I will put here top form. Top form associated to coordinate system. So I'm taking integral here, and then I'm taking integral here. And then it is interesting that statement okay, I will write it in the following way. Dx let me try to define this. There is a space integral I of omega defined by the formula star is independent on the choice of coordinate system agrees with them. How to understand it? Let us try to understand it in particular example, in one-dimensional example. Let n be equal to 1. So then what do we have? I have too many similar axes. Probably it's better to do it like this. I'm sorry, I need to redefine something. I have too many axes at the same time. I will rewrite. And I write omega in coordinates y. So here I wrote omega in coordinates y, but this measure of integration, derivative, And this is defined in terms of coordinate x. Still, I'm trying to do example n equals to 1. In example n equals to 1, I have integral over dx. Here I have omega of y. Here I have integral, Baradian integral over dx, and here I have dy. What I need to do? I need to do the following thing. I need to express y in terms of coordinates x. So y is some function of x. Dx. So this integral gives me f prime of x, because integral dx of f prime of x dx is the prime. So I'll get dx f prime of x, and here coefficient of the force dy. Let me remind you that omega was omega of y dy. And y was f of x. Now, what I can do? So this is component. And this is f prime of x. F prime, that depends on x. But this is clearly dy. So I combine these two terms together, so then I'm getting dy omega of y. So x dependence disappears. So how would it work in general? So we see that x dependence disappears, and such integral is exactly the integral that we used to think. We know. In general, we would like to write the following thing. dx1, dxn, omega I1, In of y, integral dx. And here we will have dy I1, dy In. So this is very integral. And this is the integral that you know from the textbook when you have this differential form. So you need to express this product in terms of dx's. So it will be determinant dyi over dxj. You put it here. And you will get that is exactly and this is the standard thing. So the moral of this exercise is there is an integration procedure on P, okay, Rn shifted by 1. Second, on P shifted by 1 to X, there is a canonical integration procedure. So integral omega over T1 X derivative equals to integral of omega over X standard. But in what we will do, we will not always integrate over T1 of X. Here we have a canonical measure. If we would like to integrate over Rn to 1, we need to choose coordinate. Actually, to the top form. Okay, so these were preliminaries that I wanted to tell to you before we will go to BV language. And we will go directly to BV language next time. Yes, 6 o'clock. Questions? Yes?
I'm a little bit confused about this y and x coordinate. Why there are? What's the rule of this?
So the rule was if you have E1 of X, you pick up coordinates xi. With these coordinates xi, you know how to integrate in Berezin way over the fiber. And then the rule is that if you have coordinates, you can write down the measure dx1, dxn on the base. And then the question was, what would be if you will integrate in Berezin sense along the fiber, and then with this form along the base. And what I showed to you is that the answer would be independent on the choice of these coordinates. To do it, I started with the differential form written in coordinates y. And by computation, I obtained the formula that contained no x. X kind of cancelled out of the computation.
I see. It seems you select a measure by x, by using x and select a function.
Yes, by measure, by coordinates, I selected the measure on x and on t1. And there is an integral on t1.
But you express the function on t1x by y coordinate.
I started with something written in y coordinate.
This something is exactly the function on t1x.
Yes. Because it is the differential form.
Yeah.
So this is the end of preliminaries. So I hope, so there is one thing that I have not described in preliminaries. I assume that you know what ideal is. So the only thing that I assume is that you know what commutative associative algebra is and what ideal is. And that you can get the algebra if you quotient by ideal. So it's an effect, elementary fact from the algebra. Probably I should explain it. But assuming that you know it, I think my presentation was self-contained. Okay, see you next Thursday. So I gave the homework.